Okay, happy Friday, everybody. It's uh, it's Friday today, and I'm very glad to see many of you again. This is our day two of our HeRo Summit. So I guess I don't have to waste a lot of time telling you our Robotics Institute, our Create grant, HeRo, the Healthcare Robotics Program. I think almost everybody knows. So I'll briefly tell you uh, uh, in the last episode, because it's like a movie to me, day one, we had two wonderful panels. We had industry leaders, we had physicians, we also had our faculty members discussing various issues, adoption challenges, etc. And that was day one. We also had a number of trainee talks last time on day one of HeRo Summit. Today is slightly different in that the only overlap is we still have trainee talks as usual, but this time we have three keynote speeches from keynote talks from our faculty members. All three are superstar researchers, and there's also special in that they each cover one of the three pillar areas of our healthcare robotics research. So we'll have rehabilitation, we have assistive robotics, and lastly, surgical robotics. I actually said it in the order of the keynote talks this afternoon. So we'll start with trainee talks, and very special at the end of after the three keynote talks, we'll have faculty AMA. I asked a dumb question a month ago, what is AMA? And Animus educated me means ask me anything. And I said I need to be on that panel as well. I'll answer any questions you have, although I might not know the answers. Anyhow, so that's a rich program for today. And I'll hand it over to Kimberly.
Great. Thank you so much, Sun. And also, if you missed any of the great things that he mentioned from our day one, please check out our YouTube channel because everything's posted there. For best viewing experience, under your video settings, if you want to go ahead and make sure you click hide non-video participants, that would be great. Sun mentioned our faculty AMA. Dylan, could you go back one slide? Nope, well, SharePoint is not my favorite thing. I added a last minute slide to say that we are going to be having a faculty AMA, which is, as Sun mentioned, and we were collecting questions through Slido. So if you go to slido.com, that's SLIDO.com, we're W404, and you can put your questions in now, and then they'll show up. They could also do it during the event. Go ahead, next slide, Dylan. And next slide again. We're going to go ahead and move on to our HeRo trainees. First up, next slide, is Mohammed Raisul Alam. Mohammed Raisul Alam, if you want to turn on your video and turn on your microphone, and you can go ahead and start your presentation.
Okay, thank you, Kimberly. So I'm Mohammed Raisul Alam. I'm a postdoctoral fellow at the University of Toronto. Okay. So have you ever thought about a robot that can talk to, and based on the conversation, that robot can detect diseases with memory problems? In this presentation, I will talk about such a robot that we are currently developing in our lab. Next slide, please. Before I introduce our robotic platform, I would like to talk about the population group that we are working with and our motivation to do this research. We are developing technologies to support older adults. By 2030, nearly 1 out of 4 Canadians will be at least 65 years old. As our aging population grows, an increasing number of seniors will experience or be at the risk of mental illness such as Alzheimer's diseases and dementia. There is no cure for dementia, and it has significant socio-economic impact on individuals, their relatives, and their family members. Therefore, if we can detect the disease in the early stage, it would be possible for the people, for them to plan ahead and mitigate its negative impact. Therefore, the objective of this research is to develop a social robot that can detect the onset of dementia in early stage. So the dementia is a progressive brain disorder, and that slowly destroy the memory cells, and it impact people's language skill. So so we can use, in this research, we are using the people's language impairment to detect the onset of dementia. If we go to traditionally in clinical, if we go to a physician, the clinicians use the pen and paper based methods to assess the risk of dementia. Popular pen and paper based methods are Montreal cognitive assessment tools, like MoCA, mini mental state examination, MMSE, and there are lots of tools available to do pen or paper based assessment of dementia. In figure right hand side shows the uh, clock drawing test. So in this test, so the participants are asked to draw a clock, and we assign a score based on the drawing, and based on the score we can assess the risk of dementia. So next slide, please. So we use the paper robot to implement our assessment tool. We use the picture description tags to design our system. For this purpose we use a widely used cookie theft image as seen in the left hand side. So this is the cookie theft image, and what we did actually, the robot shows the cookie theft image in his tablet, and based on initial conversation and describing the test to the user, it asks the user describe the image on his tablet, and the user described the image. The robot record the images, and we base up and we apply, and based on we extract acoustic features from the audio files that was recorded the robot, and we apply machine learning algorithm on using that features, and to classify or detect whether the user has memory impairments or not. So in the right hand side you can see the prototype that we developed in our lab. And next. Okay, this is a work in progress, and it is a work in progress, and this is our preliminary results. One of the problem of any healthcare research, I guess, is obtaining the large number of data set. So in this research, we use popular dementia bank dataset to develop our classifier. And in the top left side, you can see the figure. We use almost 80 healthy participants and around 180 patient with dementia, and the black diagram. And you can see that our data set are imbalanced, and the black block diagram shows the female participants, and the green is a green, right? Yeah, is the green diagram bar diagram shows male. So we have more. We can see from there that we have more female participants than the male. And the bottom left diagram shows the age distribution of the participants. The average age of healthy participants is around 65, and the average age of the people with dementia is around 75. Another important challenge of this research is to identify important features. For example, the features that have pathological information. For example, people with dementia tend to use more pauses than the healthy adults. So we use this feature in our machine learning classifier to identify to classify healthy versus dementia. So in the left hand side, in the right figure, we use different classifiers, and we found that a random forest classifier works better, and the current accuracy with this classifier is around 75%. So in our future work, we will improve the classification accuracy and conduct clinical trials with older adults. And that's all from. And thank you very much for your time.
Thank you so much, Raisul. Next, we have Jongwoo Kim. Dylan, if you want to go to the next slide. Yes, thank you. Jongwoo, do you want to go ahead and take it away?
Hello, can you hear me well?
Yes, I can hear you. Thank you so much.
Great. Hi, this is Jongwoo Kim. I'm also a HeRo Summit Fellow, and I'm currently doing my research at Continuum Robotics Laboratory, University of Toronto, under the supervision of Professor Jessica. And at the same time, I also research at Center for Image-Guided Innovation and Therapeutic Intervention at the Hospital for Sick Children too. So, can you go to the next slide? Yes. So my research area mainly focus on continuum soft robotics for minimally invasive surgery and also for unstructured environment. I think that one of the video at the right tab is not working. Can you press it? If it is, I mean, oh no, at the back slide. Oh, that's okay. So my work is focused on continuum and soft robot. They have a characteristics of soft, flexible, stretchable, and limitless degree of freedom. So when you think about elephant trunk, you can easily remind which characteristics they have. And it can be like defined as like actuable structures whose constitutive material forms curves with continuous tangent vectors. So as you see, like concentric tube robot is a good example of it. Even though the video is not working, it is the pre-curved nitinol tube with curvature, with super elastic characteristics. So it can make a really flexible movement. And also, there is another example, origami-based continuum robot, which was one of the other type of robot I made. So origami is paper folding techniques, and it can also give unique characteristics to continuum robot too. So I plan to use this type of a continuum robot for minimally invasive surgery, because in the past, open surgery is used for surgeons, and it is more like open to, more prone to exposure and also infections. So surgeons have used manual multi-port surgery to reduce, to minimize the exposure and also have the benefits on less infections, fewer complications, and quick recovery time. And then robot-assisted surgery is emerged, and robot, definitely can help surgeons to have a better, maneuverability and accuracy and precision. So robot can, make lots of advantages in terms of, like minimally invasive surgery, and also enhance their advantages. And I believe the next generation of the medical robot and surgical robot gonna be the robot using the Continuum robot technologies. So using Continuum robot, and we can extend its access and increase the dexterities for minimally invasive surgery. Can you go to the next slide? I think the video is not working for this slide either. Okay, so to approach it, this research topic, I would like to study mainly by 3 aspects. So the first one is modeling and control of robots. And secondly, design and mechanism of robot. And third, I also consider the applications in human-robot interactions. So it is one of my previous researches. The one is variable stiffness steerable needle. So using the needle robot whose diameter is under like a 3 millimeter, it can invade into inside of the human body and change the trajectories based on my model I made before. And also, as you see in the middle, the Tele-Operated microsurgical robot is also studied and researched. So using the haptic device, I can control the robots bi-manually, and the medical instrument can be validated and tested using this system too. And eventually, like, these techniques can used for many type of minimally invasive surgery, such as pituitary surgery and neurosurgeries. And one of the type of it, it can go through the endonasal passage. Maybe it's better, if you can see the video, but it goes into the endonasal passage and reach to the brain tumor, located inside of the head. So I work on this type of research, and if you have any interest and questions about it, you can reach me in any method, like by email, and I'm really welcome to discuss more about it. Thank you.
That's wonderful. Thank you so much, Jongwoo. I hope none of us gets a brain tumor, but I'm glad that you're working on making it easier to operate on them. Next up, we have Cidnee Liu. Cidnee, if you want to join us. Yes. Great. Take it away.
Yeah, 1 second. So hi, my name is Cidnee Liu, and I'm a master's student supervised by Dr. Mike Vanderloos and Dr. Lindia Wu at the University of British Columbia. And today I'll be presenting some of my work in developing a wearable EEG system. Next slide. So I'll start off by defining EEG, or electroencephalography. It refers to the measurement of electrical brain activity as a voltage or potential. To measure this brain activity, the subject to be measured places on a cap with EEG electrodes attached. To allow for a good electrical connection, a conductive paste or gel is applied between the electrode and the scalp. The system measures the voltage signal from different areas of the brain depending on where the electrode is placed. EEG is very useful because of its high temporal resolution when compared to other technologies such as MRI or CT scans, which have low temporal resolution but high spatial resolution. And EEG has many applications in healthcare, including diagnosis of epilepsy, sleep disorders, and dementia. EEG has also been used in the development of brain-computer interfaces, which are systems that can use a subject's brain signal to perform a task. So this can help people with neuromuscular disorders take care of themselves with less help. I have some images here showing the use of EEG in epilepsy and sleep disorders. you can see there are abnormal changes in brain activity during epilepsy, which can be monitored to detect the onset of a seizure. In terms of sleep disorders, EEG can be used to track and look at disturbances in the different sleep stages. Overall, EEG is a safe and non-invasive way to monitor subjects and patients. However, there are some issues with current systems as well. Clinical EEG systems are expensive, require long setup time, and they don't allow the subject to move around during measurements due to the wiring and hardware system. And motion can also create artifacts that mask the EEG signal or make the signal noisy, so these systems can't provide high quality data in scenarios with motion. And so this leads to only periodic monitoring and measurements, which in some cases may not be enough to capture the abnormalities in the brain signal. In cases of sleep monitoring, the system typically requires an overnight stay in the hospital with wires attached to the head, which can be uncomfortable. And while there are some clinical or research grade wearable EEG systems, most are expensive, on the orders of tens of thousands of dollars, and cheaper consumer grade systems may not provide accurate signals compared to clinical grade systems, which may hinder monitoring and diagnosis. Next slide, please. And so the high level view of this project is the development of a wearable system that can mitigate motion artifacts and provide high signal quality for research on brain activity in real world scenarios. This will allow subjects to be monitored while in motion and in the comfort of their own homes, since there's a higher likelihood that abnormalities in EEG will be detected. As well, with continuous monitoring, it will be easier to view the progression of the disorder being monitored. Currently, I'm focusing on the development of flexible low impedance dry electrodes for the EEG system and the characterization of these dry electrodes to determine the impedance at the electrode skin interface. The typical gold standard would be a gold cup or silver chloride electrode with some sort of conductive paste or gel. And this requires a lot of prep time, can be uncomfortable, and typically isn't very user-friendly. This is why I'm developing the dry electrodes, so that the procedure for measuring EEG is more efficient, comfortable, and easy for anyone to do. Shown here is a prototype of the wearable EEG system, as well as images of the traditional paste electrodes and some versions of the dry electrodes that we are currently developing. The dry electrodes are made of a polyurethane rubber, and the tips of the electrodes are coated with a silver paint. Next slide, please. And so to test and validate these electrodes, I've been using a desktop system to measure the EEG with a gold standard paste electrode and the dry electrode at similar locations on the head, and looked at the correlation between the signals as well as the power spectrum. We were able to develop electrodes with impedances in the 5 to 30 kilo ohm range, which is similar to paste electrodes, which are typically between 1 to 20 kilo ohms. And the first graph shows a comparison between the signal for the paste and dry electrode, and the second graph shows a comparison of the power spectrum between the paste and dry electrode. For the button connection type dry electrodes, the signal correlation was over 80%, which is pretty good. And so continuing on from this, we will look at using other methods to characterize these dry electrodes. For example, using impedance spectroscopy to look at the impedance of the electrodes through a range of different frequencies. And in terms of the wearable EEG system, the goal is that the device will be used not only during everyday movements and activities, but could be expanded to sports applications as well. Thank you.
Wonderful. Thank you so much, Cidnee. That was a wonderful opening to the HeRo trainee presentations. Now we're going to interrupt for a moment and have our first keynote speech on the rehabilitative pillar. And Rosalie will introduce our keynote speaker. Rosalie?
Hi, everyone. So really great to see you all. Yeah, so it's great to be here on day 2 of the HeRo Summit. It's my pleasure to introduce to you Dr. Alex Mihailidis. He is not here in person today, which means that I can say whatever I want about him, but no, that's No, I'm just kidding. Alex is a professor in the Department of Occupational Science and Occupational Therapy and the Institute of Biomedical Engineering. And he is the Barbara G. Stymius Research Chair in Rehabilitation Technology at the University of Toronto and Toronto Rehabilitation Institute. And he is the Scientific Director of the AgeWell Network of Centers of Excellence, which focuses on the development of new technologies and services for older adults. And in addition to that, he is the Associate Vice President of International Partnerships at the University of Toronto. And so it's a great pleasure. He's a world-renowned researcher in assistive technology for older adults with cognitive impairments, smart home systems, intelligent systems, artificial intelligence, and robotics in health, rehabilitation, and wellness. He's also an award-winning teacher and a mentor of trainees and a true champion of his colleagues. It's an honor and joy to work with him. I hope you enjoy his presentation and take up his offer to chat with him at any point. So send him an email if you would like to chat. So, all right, thank you.
Sorry about that, everybody. Just figuring out how to share sound.
Today, I'd like to talk a little bit about what we're doing in the area of robotics for rehabilitation, and specifically what is happening over at Toronto Rehab and members of the Robotics Institute that are also scientists there. Before I move on, I'd like to first acknowledge the team members who have all contributed to this work and to this presentation. Dr. Aaron Yurkovich, who's a former doctoral student with us, Dr. Rosalie Wang in the Department of Occupational Therapy, Dr. Raisul Alam, who's a postdoc fellow with us, and Dr. Jose Zarifa, who's a scientist at Toronto Rehab and a professor within biomedical engineering. I also like to acknowledge Professor Debbie Hebert, who passed away last year. Professor Hebert was a OT and a practice lead at Toronto Rehab, and she really was the clinical lead and inspiration for all the work that you're going to see here today. So first of all, what is Toronto Rehab, or KITE, which is the new research institute? Toronto Rehab is Canada's largest academic rehab hospital for adults across 6 clinical programs, as you see right centers in the world with respect to rehabilitation, and technology plays a key role.
I'm sorry, pardon us. We're just going to switch over to a different feed and see if that works.
Alam, who's a postdoc fellow with us, and Dr. Jose Zarifa, who's a scientist at Toronto Rehab and a professor within biomedical engineering. I also like to acknowledge Professor Debbie Hebert, who passed away last year. Professor Hebert was a OT and a practice lead at Toronto Rehab, and she really was the clinical lead and inspiration for all the work that you're going to see here today. So first of all, what is Toronto Rehab, or KITE, which is the new research institute? Toronto Rehab is Canada's largest academic rehab hospital for adults across 6 clinical programs, as you see right here. But perhaps most importantly for this presentation is the fact that Toronto Rehab is also one of the largest and best research centers in the world with respect to rehabilitation, and technology plays a key role here. In terms of who we are scientists who are dedicated to improving the lives of people living with the effects of disability, illness, and aging. More specifically, our research focuses across 3 different areas. This includes injury prevention, restoration of function, and enhance participation in independent living. As you can see, at Toronto Rehab, we actually have a very wide-ranging definition of rehabilitation. We believe rehab doesn't start just right after your injury, but actually starts with injury prevention. Now, some of you may have seen the various facilities we have over at Toronto Rehab Kite. For example, we have Street Lab, which is shown in this top corner here, which allows us to do a 360-degree visual surround of a streetscape that we can build, and hence allowing people to interact with the environment as they're perhaps walking down the sidewalk or something. We have Driver Lab, which is our newest research lab, and this is a fully automated driving simulator with, in fact, an actual car that is in the lab itself. We then have Winter Lab, which allows us to do things such as test winter footwear, winter clothing, the mobility of various types of assistive technologies on ice surfaces and other things. Stair Lab, it does a lot of work around standards to develop different things such as handrails and the size and scope of stair design. Home Lab, which is the primary lab that my group works in, is a fully simulated house that allows us to do work around smart home research, etc. And finally, there's Care Lab, which simulates a full patient room. And as a member site of the Robotics Institute, you all have access to these facilities. As you can imagine, ones we can reopen because of COVID. So let's get specific to how we're using robotics in rehab and at Toronto Rehab. So we're focused on helping our clients maintain, return, and enhance their abilities to engage in daily activities. And this may be anything from self-care activities to something that we take for granted without a disability, such as preparing a cup of tea or making a meal or changing our clothes. Within the area of rehab robotics, we are looking at a variety of areas specific across two areas: physical rehab and cognitive rehab. Our work in physical rehab has been going on for many years. The work on cognitive rehab is brand new, and so I'll show you one of the projects later on in this talk. So let's start with physical rehabilitation. So physical rehab can cut across a wide range of various aspects and injuries, anything from spinal cord injury to what we focus on, and that is stroke. Now, the current state of physical therapy in Canada for stroke rehab is actually not that great. Typically, most of your therapy happens in the first 6 months. We then have problems in terms of access to stroke rehab once you are discharged from the hospital, you return to home. Obviously, we have disparity across socioeconomic statuses. We have disparity across geographic locations and others that we're looking at. In terms of the paradigm or the spectrum of stroke rehab, typically you start as an inpatient, then you move to an outpatient. Hopefully at that point you're getting community-based rehab, and then beyond that, and typically after those 6 months or 7 months, it's all about home-based rehab. Now, the problem with stroke rehab is it's difficult. As you can see here in this picture, typically it involves common objects that you find around the physical therapy gym or in your home, and you're really doing makeshift ad hoc exercises to mimic the type of rehab you would formally receive while you're in the hospital. If we have to summarize stroke rehab, though, why it's so difficult, basically it is very repetitive, it's very labor intensive. It's limited to one-on-one therapist-patient time, so it's very difficult for a therapist to work across multiple patients. There's various economic pressures within the hospitals, especially these days. And then when you get to home rehab, it is self-directed, and there's very little professional or quantitative feedback. And so because of that, what we actually see is very poor exercise adherence at home. As you can see in one of the studies here, it's about 65 adherence to at least some part of their therapy. Now, because of this and the need to perhaps quote unquote automate some of this therapy, the role of robotics is actually starting to be recognized in various practices. So for example, if you look at the stroke best practices that were developed in Canada a couple of years ago, they actually have a section around how robotics can play a role in providing therapy. And again, here's a quote: robotics are an emerging developing area in stroke rehab programs should begin to build capacity to integrate robotic technology into stroke rehab therapy to appropriate patients, as the research evidence suggests, and in the future incorporate this therapy as part of comprehensive therapy where available. Now you notice there are 3 parts here that are highlighted, and it really is about capacity, understand the type of patient we're working with, and how to provide this therapy where and when robotics will be available. So as probably most of you know, rehab robotics is nothing new. There's actually been a lot of research being done on this area for at least a couple of decades. There have been a variety of robots that have actually been developed, as you can see, some examples on this slide right here. In fact, we're actually now at the point where you can buy a rehab robot on Alibaba. You just go ahead, you don't need a prescription, you don't need a physical therapist, and you can go ahead and just buy this exoskeleton here to do upper limb rehab. Now, as you can imagine, beyond some of the challenges that you can think about right now without having a therapist involved in any of this, one of the primary issues with rehab robotics is that they're very, very expensive. The rehab robots I showed on the previous page, this one, others that are out there, typically are anywhere from $100,000 up to $500,000 US if you want to include all the bells and whistles. So as you can imagine with this price point, rehab robots are not being purchased by hospitals across the globe right now. At Toronto Rehab, we have 1 or 2, which are prototypes we built. Across the city, there are actually very few number of rehab robots that are available. And this is very similar across other major urban centers and hospitals. And as you can imagine, rural locations where perhaps rehab robots can have the greatest impact, there are none being used right now. So in the work that we're doing, one of the main things we want to do is to increase the value add of robots. And this includes coming up with better ways to quantify performance changes in order to show how robots can be superior to current clinical measures, and using the various sensors on robots that will allow us to collect more data. The value add that we're also adding, obviously, making them more motivated. We're working with various researchers and companies in game design to help come up with more engaging games and interfaces to encourage, but more importantly, to provide real-time feedback to the patients. We're trying to make these robots adaptive and intelligent so that therapists do not need to be constantly present. We're not saying to cut the therapist completely out of the loop, but to make the robot itself using things such as machine learning to adapt its exercises automatically. And the whole goal of this is that, the therapists then don't have to sit there and do that back and forth arm motion with the patient over and over again. But then after the robot provides that kind of training, therapists can focus more on the functional activity training and the community integration as well. Now, the other major value add here is obviously cost. So one thing I will talk about later on is how do we drive the cost of these robots down from hundreds of thousands of dollars to ideally only thousands of dollars, or better yet, hundreds of dollars itself. So before I talk about some of the work that we're doing around rehab robots, just to show you that there is also some strong clinical evidence that shows that rehab robots can actually have a positive impact on the clinical indicators for people with stroke and even other types of injuries as well. Here are 2 some of the major studies that are out there. One is a Cochrane systematic review, and the other one is a systematic and meta-analysis of all the types of clinical trials that did occur. And I'm not going to go over the data here in detail, but basically what you see here is that there has been improvements in such things as arm muscle strength, arm function, and the completion of generic activities of daily living. And there's also been improved motor control, significant but small according to the study, and again, also showing changes in muscle strength. Now, when we started off our project a few years ago, we wanted to start with a very user-centered design approach. And so the first thing we wanted to do was to really understand, what do clinicians want? What do clinicians want to use the robot for in their therapy, and what functions and features do they want it to include? So we went out, we did very large-scale international surveys across many different countries, also including physical therapists and occupational therapists. And what we found, obviously, is things such as in terms of aims of rehab, obviously, a lot of them show that it's very important to facilitate functional activities, prevent further injury or complications, improve coordinations, and other aspects that help to learn normal muscle movement. Now, in terms of facilitation of movement and some of the functions and features that therapists want to see in the robots, again, we saw them strongly agree or somewhat agree across a variety of task functions. For example, that needs to be task-oriented training and practice, that the stroke survivors still need the one-on-one therapy sessions. However, that robots can also provide some of that aspect. They want the robotic devices to perform these repetitive tasks in a single training session with a clear functional goal. And obviously that they also agree that robots can provide some high intensity focused therapy. So with respect to the work we started, we have done work on robotics on 3 areas of the upper limb or the arm. And where I'm going to start is with the upper arm part, which, as you can see in this shaded diagram, includes the shoulder, the elbow, the biceps, right down to the wrist. So we developed in partnership a rehab robot that can provide range of motion and power a fully functioning arm. It has very low inertia, friction, and backlash based on the design that we went through, which I'm not going to get into. We want to make sure that we reduce its size and its weight. None of the robots that I've shown you before can actually be picked up by physical therapists and moved from patient room to patient room. The one we designed can be. We want something that's easy and safe to set up, and most importantly, affordable. And we aim this to be in the area of $10,000 to $12,000 Canadian. So this is a picture of the 3rd generation rehab robot that you can see. Basically, it is a tabletop robot with an LCD monitor on top that provides various games and motivation and feedback. It has a fully haptic robotic arm that provides force feedback, it provides resistance, but it also provides assistance as well. In terms of the design, we worked with a local company called Quanzer in order to drive the cost down. And so we worked with them to come up with a very simple mechanism approach that reduces as many moving parts and the use of various expensive motors as needed in order still though to provide a fully powered robotic device. Now at this point, I'm going to show you a video where you're going to meet Dr. Rosalie Wang, and she'll talk a little bit about what the robotic device does.
Feel about doing this type of study. And I'm also looking at another program that is an intense therapy program combining robotics and homework and goal setting for clients.
So this is our stroke rehab robot. So it sits with a wide open workspace, and it has a robotic arm that the patient can use to do exercises. The arm can move really freely, or it can give assistance or resistance when meeting a target. So therapists can set up exercise programs tailored to the individual patient, with targets aimed to promote natural motion, to extend range of motion, and to build strength. The system produces a variety of reports that can be reviewed by the therapist and the patient that track progress over time.
Receiving therapy as soon as possible after. We'll just skip that guy because you're getting enough of him right now in the presentation. So we went through and we conducted various clinical and usability studies of that rehab robot. And just to give you a sampling here, the main measurement that occupational therapists and physical therapists use for the upper extremity of the arm is the Fugelmeyer Scale. And as you can see over time with this particular participant, there was an increase in terms of the Fugelmeyer score. It was small, but it's still clinically significant. And also we saw an increase in active range of motion. You see the same thing for participant 2 here as an example, where we see overall an increase in their functionality. Now, some of the other key findings from the studies that we conducted about 4 or 5 different studies across the different types of robots we built for the upper arm. Is first of all, with respect to usability in outpatient studies, it showed that robotic therapy with a therapist is enjoyable, useful, and safe. What we also found is that with a robot, about 1 hour a session, 3 to 4 times per week, was manageable and was satisfying for chronic outpatient stroke survivors. And as like with any kind of pilot study, we currently have low sample size, but we have more studies to come. But what we're starting to see are possibly moderate positive effects. We're also trying to understand the need for more task-specific hand and wrist movements, as I'll show you, and whether this is actually possibly too staff intensive. So one thing we heard from some of the therapists in the hospital that were using the robot is that it took a lot to set up the device, to get the patients going, and then to monitor what they're doing. So that's something we want to work on as well moving forward. Now, as we move down the arm, one thing we did is we wanted to develop a module that would just connect to the existing upper limb robot that would provide also wrist and lower arm activation and increase in strength. So what we developed is this little device you see here with a support glider on it so that you can actually still do wrist exercises along with the upper arm. And then we have a fully haptic handle that allows the person to do the various exercises. So once again here, what I'll do is I'll show a video of this device working. So as you can see here, the person is doing their various exercises to assess what their current range of motion is. The person would also have some kind of visual feedback, like with the overall device you see here. And then in terms of exercises, similar to the upper arm robot itself, the person is watching a game here and is doing various types of wrist motions back and forth. Now, in terms of some quick clinical findings from the study we completed with that device itself, again, if you look at range of motion with respect to clockwise and counterclockwise, we do see increases with our participants from the robot itself. And if you look at the amount of torque that the person can apply through the wrist, again, we're seeing increases from the use of the robot. Now, the final robot we developed for the upper limb was around the hand. And this was something that therapists brought to us and said, you know, this is great that we can get the upper arm going, but if they can't use their fingers, if they can't get out of the typical grasp that they're in, which is this post-stroke, then they can't actually do anything functional. They can't pick up a glass, they can't get themselves dressed, they can't bathe themselves, etc. And in fact, this is actually a big problem, as you see on this slide right now, that 1/3 of stroke survivors actually do not regain hand function in order to complete daily activities. On average, they state they have at least 5 unmet occupational needs, and 83% of survivors report a significant decrease in quality of life because of poor hand function. So this was the work of my former PhD student, Aaron Yurkovich, who's a postdoc now in the UK. And he wanted to take a truly user-centered approach and also an open access approach to this as well. So he went through various iterations where he just iterated very, very quickly. He would build prototypes, devices that would be wearable to help with hand function, exoskeletons. He built things out of Lego, etc. And all along the way, he would do very rapid usability testing with patients, with therapists to get their feedback and to continue to iterate his work. Now, in terms of what he developed, and I'll show you a video of Aaron talking about this in more detail, is what he calls the HeRo glove. So the HeRo glove itself assists hand opening and enhances grip strength through various types of motions. You can see here that there are these strips that help to bend the fingers into a grip position, for example, led by some motors. And then again, on the palm side as well, there's some activation that's allowed that can actually help open and close the hand as needed. Aaron made sure that it was portable, affordable, and easy to use. And as I mentioned, this was all open hardware and open source. In fact, right now with his final design, we have about 60 or 65 therapists around the world who have downloaded the schematics to build their own hardware, and then Aaron has provided the software. So I'm going to show you a video here. This is an actual patient. We do have full permission to show him as part of this video. And as you'll see, if using one of the prototypes itself, he's able to complete various typical functions. This is one of the common tests that are completed. You have blocks and place them in a pattern. Without the device, obviously, you will not be able to put any of the blocks. With the device itself, manually activating right now, is allowing it to pick up these objects. Again, demonstrating some very common activities, such as holding a bottle to pour. There, his hand function is so poor, he did need some assistance from a therapist. Right here, obviously grabbing and folding towels, so doing something simple as laundry. The device allowing him to do that. Something as simple as using a phone that he would not be able to do before in order to eat a meal. And again, the hand glove itself is allowing him to maintain that grip. So again, through Aaron's results clinically, he found that with the glove, people are able to complete more activities, more tasks, such as the ones you saw in the video itself. In terms of things like finger extension, range of motion, we saw significant increases in the number of degrees that the person was able to go through. Grip strength, we saw significant changes where basically with the robot, they had some grip strength. Without it, they basically had nothing. With the box and block test, which is shown in this picture here, without the device, they weren't able to do anything. With the device, they're able to move 3 blocks, and you'll see some other activities here. Now, the one thing is the satisfaction. So basically with across these 11 participants, they rated a 3, which is more or less satisfied. So again, this is something that Aaron took into account to further iterate the device itself. One of the next things that Aaron has been working on now part of his postdoc is more automated ways to work the glove. Before, we had a very simple sensor in there that would detect when the person moved their hand and then stop, indicating that they wanted to close their hand, and then moving again, indicating they want to open it. What Aaron is now looking at is myoelectric devices that uses obviously electrical signals from the muscles in the arm in order to operate the gloves.
Soft wearable robots are advancing and merging the fields of rehabilitation and assistive technology to help millions of people recover hand function after stroke. And now squeeze as much as you can. And now relax. And now extend. And now relax. Squeeze. HeRo is an untethered myoelectric controlled soft robotic box. It provides 5-finger grip assistance when the user attempts to grasp, and 5-finger extension assistance when the user relaxes the shoulder, elbow, wrist, and hand. 9 people with severe hand impairment after stroke completed a hand function assessment and 13 daily living tasks, like holding a phone or toothbrush, doing up a zipper, and cutting food. With HeRo, all 9 participants surpassed clinically meaningful important differences on the hand function assessment, and 4 surpassed these differences on the daily living tasks. 9 participants incorporated their affected hand into more of these daily living tasks and performed them more independently.
Like that. Yeah, I've never been able to do this.
The majority of participants were satisfied with HeRo and found it to be useful and easy to use. 7 participants desired to use HeRo in the clinic and at home during their therapy and daily routines. Our developments and findings provide therapists and people after stroke with exciting opportunities for integrating myoelectric soft robotic gloves into their rehabilitation programs and daily routines. This will enable
So Dylan, maybe you could advance the slide.
Nope, that's not working either. I don't know why it stopped.
This is really truly open source in terms of the hardware and the software itself. So I'll finish off now by showing you one of our brand new projects where
Technical difficulties, pardon us. Let's see if we can catch that last few minutes.
in terms of the hardware and the software itself. So I'll finish off now by showing you one of our brand new projects where we're trying to use robotics in cognitive rehab as well, primarily for people with dementia. So people who may have dementia or Alzheimer's disease or suspected Alzheimer's disease has to go through a variety of assessments in order to determine if they actually have the disease or not. And again, as we all know, this is really truly not known until a person is deceased and they can do a post-mortem and they can actually see the shrinkage in the brain itself that shows Alzheimer's disease. However, one thing that is well known in studies is the impact of cognitive impairment on language problems. And what we see is as a person's cognitive impairment increases, obviously they're going to have greater language problems as well. Now, this has been used not only obviously to see if a person is progressing, but to assess a person's level of cognitive impairment to determine whether the person may have dementia or not, and also then to perform rehabilitation to help the person improve in some of those language functions and speech areas. What I'm going to show you here is an example we're doing with another researcher, Frank Rudzik, who is very well known here at U of T and around the world in terms of speech recognition and a lot of the work that he's been doing on doing things such as having an older adult with dementia just describe back what they're seeing in the picture and then automatically analyzing their speech to determine whether the person may have dementia, the level of severity of the cognitive impairment, and again, to apply rehabilitation. So we've been working with Frank to apply that to a robotic platform. Many of you may recognize Pepper here. And so what I'll do is I'll just play the video so you can see how well it's working.
My name is Pepper. Today I will be guiding you through a simple test to screen for dementia. In a few moments, I will show you a picture on my tablet. All you need to do is describe what you see. Let's get started.
Doing the dishes. And he's into the cookie jar for his sister. And she let the water run over in the sink.
Great job. Thanks for doing this together with me. That was a lot of fun. While we wait, let me tell you more about this test. Just now I showed you a picture on my tablet and asked you to describe it to me. Your response can tell us more about how you express what you see. Sometimes we can use these results to screen if someone may be at risk of developing dementia. Remember, the results of this test are only for screening, so you will have to see your doctor for more accurate results. Thank you for your patience. Your results show some differences between other healthy participants. Since this is only a screening, it might be a good idea to speak with your doctor for more accurate results.
So as you saw there, basically the picture was displayed. Pepper listened to what the person was saying, and then using the algorithms and approaches that Frank Rudzik and his team have developed, we did an automatic analysis, and the robot provides the information back. So the next study we actually want to do in this area is to determine, does an embodied approach like this improve the usability, the satisfaction of using this type of device as opposed to just doing over an iPad. So we are looking at various modalities as well moving forward. So to finish off, in summary, hopefully you've enjoyed seeing some of the examples of the work we're doing with robotics in the field of rehabilitation. That's part of the Robotics Institute. As I described, rehab robotics is not a new field, but it's only really recently, as we're starting to see more devices and the price of these things come down, that they're starting to gain traction in clinical applications and settings. However, we still need to move towards new design approaches in order to ensure that we're meeting the needs of our clients and the clinicians themselves. So user-centered design approach really is important to continue to move forward. However, at the end of the day, no matter what we build and all the great work we do and all the cool devices we develop, cost is going to be the primary limiting factor. Hospitals have small budgets for technology, if any. Home healthcare networks and companies, again, have very small budgets, especially these days with everything that's going on. And so we really need to be figuring out, how do we move these technologies from these very expensive healthcare devices to new consumer-driven approaches and devices. And I show one picture here of one of these new fads, which are kind of these walls or these mirror devices to help you do exercise. And I show this not because this is a good example of something, but it is actually a good example of the way they have moved exercise equipment into everyday furniture, essentially, and part of everyday living. And at the same time, how they're driving the cost down. And in my opinion, this is the same thing we need to do in the rehabilitation field. We need to take these devices from looking very medical-based, as I said, high cost, and turn them into something that's elegant looking, like the picture you see here. It will only be at that point that I feel that we'll get true traction in the area of rehab robotics. But thank goodness here at the Robotics Institute and University of Toronto and our affiliate hospitals, we're all working towards this problem. So with that, I thank you very much for having me. Again, I apologize I can't be here on Zoom with you to answer any questions, but please feel free to email me. My email address is at the bottom, along as our lab web address, my Twitter handle, and I look forward to ongoing relationships and being part of the Toronto University of Toronto Robotics Institute. Thanks very much, everyone.
Thank you so much, Alex. Dylan, if you want to get us back on track, let's have some HeRo trainee presentations. Yes, that's great. And first up, we have Zhiling Zhao. Zhiling, are you here?
Yes, can you hear me?
Yes, perfect. Hey, Zhiling Zhao, go ahead and take it away. Thank you so much.
So hello, everyone. My name is Zhiling, and I'm a first-year biomedical engineering master student supervised by Dr. James Drake and Professor Jessica Bergenkars. And I'm going to present about the project Concentric Tube Robot Path Planning for Epilepsy with 3D Slicer. Next slide, please. So epilepsy is a neurological disorder which affects more than 15 million people worldwide, with 30% of patients requiring surgical intervention as primary treatment. Recent studies have shown major advantages of robotic surgeries on reduced pain, recovery time, and scarring. So for each procedure, the surgeon usually needs to manually define the possible incision approaches for each patient. However, it is difficult to optimize for multiple criteria using manual placement. So therefore, the goal of the project is to bring necessary components together to implement a simulation, planning, and optimization system for tele-operated epilepsy procedures. So the platform the system would be based on is 3D Slicer, which is an open source software that is developed and improved by multiple institutions worldwide. It is very powerful in terms of image processing and 3D visualization. So the tele-operation is achieved using a haptic device on Phantom Omni. It provides transformation matrix of the stylus and have useful functions, including virtual fixtures. Last but not least, I would like to briefly touch on the tool, Concentric Tube Robots. It is a class of continuum robots that consist of nesting, pre-curved tubes that are each made of elastic material and fit concentrically one inside the next. So each tube can slide and rotate with respect to each other. And the advantages of concentric tube robots include their flexibility, smooth curve motion, small size, and so on. Next slide, please. So the major components of the system are a planning and optimization module and a simulation module. So input to the planning process is a 3D model of the important anatomy and the robot model, where anatomy model is segmented and reconstructed from the patient's MRI DICOM images through interpolating between slices. The planning process is iterative. First, the optimization problem is formulated based on anatomical constraints and the robot parameters. And optimization goal is to maximize the resection volume. As multiple incision sites are possible, multiple good solutions may exist. Second, the solutions are translated into robot-specific plans, use robot kinematics. And after the translation, the surgeon can select the path either based on the algorithm suggestions or based on menu selection. If the result is not desired, inputs can always be modified and start the process again. Next slide, please. So the simulation module would be consisted of haptic device interface and the visualization module in 3D Slicer. The interface is constructed using Plus, a server toolkit for data transmission, and the server is specifically configured to use the haptic device API to collect movements of the device's stylus, as well as the state of the button on the stylus. Some simple data processing like frequency filters were also applied before sending the data to Slicer to improve the quality of the recorded data. Data received in Slicer is in terms of transformation matrices that contains the haptic device's information, which can be translated into position and orientation of the tip, which can be further translated into robot joint parameters using inverse kinematics, and robot configuration can then be simulated using its forward kinematics. And another important feature implemented in visualization is collision detection, because touching certain anatomical structures like vessels need to be warned in teleoperation. And an example of collision detection is shown on the right. Picture at the bottom shows a sample simulation window with 2 trajectory views, 1 endoscope view, 3 standard views, and 3D visualization. And that wrapped up my presentation, and thank you very much for listening.
Thank you so much, Zhiling. That was lovely. And next up, we've got Mehdy. Dousty, are you here? Great.
Yes, I'm here.
Go ahead and take it over.
Okay, thank you very much. Hello, everybody. Welcome to my presentation on postural analysis of the hand in individuals with cervical spinal cord injury using egocentric video. My name is Mehdy, and I'm a PhD candidate working under supervision of Dr. Joseph Zarifa and Dr. David Fleet. Next slide, please. Spinal cord injury, or in abbreviation SCI, is an unexpected and devastating medical condition that changed the course of a person's life. Studies ranking the preferred function priorities for individuals with spinal cord injury reveal that the improvement of hand function is a top priority. So given the importance of the restoration of hand function, particularly hand grip after CI, studies on the assessment and rehabilitation of the hand are important. The current clinical assessment relies on direct observation in clinical environments, and it doesn't reflect an individual's performance at the home. In other words, there is no information on the types of dexterity and patterns of manipulation used in various activities of daily living at home, which prevents us to have a clear and individualized design goal for a hand robotics, and also prevents us to examine the impact of new robotics rehabilitation technology at their life. Therefore, new outcome measures are needed to describe different domains of function in non-clinical environments. Next slide, please. Among all of the wearable technologies, wearable camera has a substantial potential to capture hand complex movement and also provide a platform that can be used to integrate multiple analysis, such as functional interactions and hand postural analysis. However, processing large amount of complex video data manually is incredibly difficult, emphasizing the need for automated data analysis. In the image in the slide, some examples of egocentric frame recorded at participants' home are shown. So our objective here is to build an algorithm that summarizes hand postures and grip strategies observed in egocentric video. The result will be used to generate a report to be interpreted by a clinician. In this presentation, I'm going to talk about 2 recent published papers. In the first study, we showed that the proposed method is able to track the use of tenodesis grasp. Tenodesis grasp is a grasping strategy that enables people with SCI to passively close their fingers using wrist extension, and thus can be used as a compensatory approach by those with reduced finger strength. Quantifying the use of the posture is an important consideration when assessing the impact of rehabilitation interventions. In the figure, we provide two examples in which one is using tenodesis grasp and the other is not. Our proposed architecture is shown in the study 1 section. After having an input image, we use object detection algorithm, YOLO-V2, to estimate hand locations. Next, we use open pose, which is a pose estimation algorithm to estimate 21 joint coordinates. Next, we design a new algorithm to estimate arm orientation, leading to estimate rest angle. We quantified the performance of the method using 17 participants. Our result showed that the method can provide a clear indication of which participants relied on tenodesis grasp, as is shown in the figure. Next slide, please. Tenodesis grasp is only one of the many hand postures that may be used by individuals with SCI. In the second study, we examined the potential of the method to cluster various hand postures using egocentric video. The architecture is quite similar to the first study. Particularly, first we localize hand and then estimate joint coordinates. Next, we use clustering algorithm to categorize similar hand postures. And finally, we examine the performance of the method. There is no single best clustering algorithm in general. Different algorithms are appropriate for specific problems. Therefore, we need to examine different methods to identify the best possible approach. A large number of clustering algorithms were tested, and the results show that Gaussian mixture model and spectral clustering acquired the highest performance among the examined methods. Cluster 1 and cluster 2 in the results sections show 3 frames belong to the same cluster. Currently, we are working to refine the hand posture representation to obtain more precise clustering distance function to boost the performance, the method performance. Thank you very much.
Thank you so much, Mehdy. I'm thinking about my hand postures now. And next up, our final HeRo presentation today, Meena Fatah. Meena?
Yep. Hi, everyone. You can hear me all right? Yeah. Okay, awesome. My name is Meena Fatah. I'm a graduate student under the supervision of Dr. Robert Hamilton and Dr. Mike Seed at the Hospital for Sick Children, and under the supervision of Dr. Hamilton again and Dr. Yusen under the Answer Create HeRo program. So today I'll be talking about my project, which is elucidating the role of autoantibodies in the pathophysiology of Brugada syndrome. Next slide, please. Brugada syndrome is an inherited rhythm condition. It has a prevalence of about 1 in 2,000 and is responsible for about 20% of sudden cardiac deaths. The current gold standard for diagnosis is the Shanghai criteria, which diagnoses individuals across a series of clinical categories, of which in the center of the screen, the ECG that you see is required for a diagnosis. Unfortunately, though, this ECG manifestation is transient and not always present at rest or baseline. And in some individuals, they have to be given drugs to bring this ECG manifestation out. Adding to the complexity of the disease is its genetics. It's inherited in an autosomal dominant and incompletely penetrant manner, meaning that where an individual has a pathogenic mutation for it, they have a 50% chance of passing it on to an offspring. But even when an individual has a mutation, it doesn't necessarily mean that they'll develop disease. And the only known pathogenic mutation only accounts for about 30% of cases. So in the other 70% of cases, we wondered, could it be novel genetics or secondary pathologies that are at play? Next slide, please. So in the far left, we've actually published in June of 2020 that indeed there are secondary pathologies at play. We discovered autoimmunity in individuals with Brugada syndrome, which is essentially their immune system creating antibodies against proteins that are their own. And this doesn't happen in healthy individuals. And what we found was that for some reason, and we're not quite sure why, individuals with Brugada syndrome created antibodies against 3 cardiac proteins: alpha cardiac actin, 1, keratin, and connexin 43. So in order to I have a little bit of a better understanding as to what these antibodies did from an electrophysiological perspective, I created an active immunization model, which on the bottom left, you'll see a little picture of a mouse. Mice were injected with the 3 proteins that we found autoimmunity against, and they were allowed to create antibodies against these proteins. I then conducted ECGs on these mice and compared them to controls. And on the top right, we see 3 graphs. So in the far right, QRS duration, this is a measure of depolarization, so how negative the cells are able to become. And what we note and what we can appreciate is the pink there, being a protein-injected mice, is having a little bit of a longer duration as compared to the other mice. We move to the center graph, QTC duration. This is actually a measure of depolarization and subsequent repolarization. And also interestingly, in the same mouse, we see that it's lower. And then finally, we look at index of cardioelectrophysiological balance. And this is actually an index that allows us to measure the chance of dangerous arrhythmias happening, like ventricular tachycardia and fibrillation that can lead to death. And interestingly, a low ICEB index is also clinically associated with Brugada syndrome. And once again, we see that it's quite low in the same mouse. We take a look at the bottom black image there, the co-localization of IgG. This is essentially just showing that in the same mouse, that pink mouse, we see that only one antibody actually bound to the surface of heart cells, and that was interestingly connexin 43. Now, connexin 43, that's just an image of that's just an amino acid sequence of the protein. It's a very important protein where 6 of them actually create half of a channel, and you can kind of think of it as one channel on the edge or surface of one cell and another half channel on the other, and connected it creates a tunnel called a gap junction, and this gap junction is essential for cell-to-cell communication. So for some reason on our sick mouse there were antibodies affecting or created against that protein. Next slide please. And so my question for this puzzle piece of my project is, are anti-connexin antibodies contributing to the conduction changes we see in the mice and also in Brugada syndrome? The objective of the study in this particular part of it is to examine if indeed we can take a look at these antibodies, put them in an environment where we can study their effect on electrical conduction. And one of the ways that we can do this is through an in vitro cell model, or taking a look specifically at iPSC-CMs, which are induced pluripotent stem cells that are coaxed into cardiomyocytes or heart cells. So on the right, we see one of the 2 techniques, the automated robotic techniques developed by Dr. Yusun's lab. And this is actually a dye injection technique where we take a plate of adherent cardiomyocytes and we expose them to something. And in my case, they'll be exposed to connexin 43 antibodies and compared to controls. And we inject cells with a fluorescent dye. And the number of adjacent cells that are actually able to pick up this dye gives us an idea of gap junction intercellular communication, and we can compare this to normal controls. On the left there, what we see is conduction velocity, and this is another measure for and another robotic system that Dr. Yusun's lab has developed that we'll also be taking a look at for this assay. And conduction velocity is an important measure of the speed and direction of an action potential. And with a lot of arrhythmias clinically, we see differences from normal in their conduction velocities. So it's going to essentially also be a plate of cells. These cells will be paced and they'll be exposed to connexin 43 antibodies compared to controls, and we'll be able to see using this measure if this conduction velocity is actually affected by the presence. And conduction velocity is cool because not only does it measure gap junctions like the dye, but also gives us an idea as to ion channels, which are very important also in conduction velocity measures. So this is really just one puzzle piece of the large project that I'm doing, but I felt like this was the most applicable to robotics and engineering. But yeah, that's all for me.
That's fantastic, and that was very well said. I really appreciated that. Right now, we're going to take a very short break. We'll be coming back at 2:30 to have our keynote on the assistive pillar with Goldie Najat, and Yusun will be introducing at 2:30. So we'll see you in just a few minutes. Thanks.
You and all the members of the organization for inviting me to talk here. It looks like it's been a really interesting day, and I'm really looking forward to watching the Robotics Institute blossom the way it has all the promise to do. So I'm actually dressed like this because I'm about to go up to the operating room, and I think I'm going to miss the other session. and do a neurosurgical operation for which I wish I really had a robot. And so we're going to do a procedure that I'll show some videos of with mechanical tools that have been around for about 50 years. And, you know, it's going to be a relatively safe operation and it'll likely be successful. But I know that if I had the robot that we've been working on for these past years, that we could do it faster, safer, and with a better outcome. And so that's the sort of thing that we're trying to do at Cidnee. And, you know, Cidnee was already a mouthful, and I'm very happy to announce actually that we're now the Wilfred and Joyce Poslan's Cidnee, after very generous donation from a family to name our group. So we're very happy with that. And I noticed that Andrew Goldenberg is on the next AMA discussion, and he and I have been at this for a long time, like 30 years. And this was a robot we designed in the early 90s to do neurosurgery using an industrial Puma robot. And what was the stereotactic frame at the time? This is what the graphics looked like. We wrote our own graphics. We wrote our own computer interfaces. We brought this up into the operating room, and we did 4 operations with it. And very quickly, it was surpassed by a passive robotic system that I'm showing here. And the graphics improved phenomenally. And now every neurosurgical procedure virtually is done with image guidance of some sort. So not robotic systems necessarily, but image guided using relational databases and reference systems. So it's become pervaded throughout the neurosurgical community. And medical robotics is really starting to, I think, take off. And I'm just showing here some of the more neurosurgical robots that are currently in use. The Da Vinci has not been used very much for neurosurgery, but is used throughout the world. These are more recent neurosurgical robots, and the commercial market for these is enormous. And so I think there's a huge potential in the medical robotics area. And this is another very simple neurosurgical robot that we now have in our hospital, and it puts a laser fiber into the brain for us to treat very small lesions at the very center of the brain you see here. So these are very hard to get to by any other means, and we do the whole operation in the MRI suite, and the temperature in the lesion is monitored throughout the procedure. So this is where the whole area, I think, in neurosurgery and in other areas is going. So minimally invasive, image-guided surgery, and this is where I think what is really important, and why I'm so pleased to be part of this, because I think we need an interface between the clinicians and medical people and the engineers and scientists to come together to design things that people really need. And this is a book that we wrote several years ago with Waleed Farhat, who's a urologist, and those are 2 of our MD PhD students who came through Cidnee to work on projects having to do with robotics. And so that's what I think the future looks like. And this is what we have been concentrating over the last decade. So developing minimally invasive robotics tools, working on simulation and modeling, and image-guided procedures using MR-guided focused ultrasound. And this is the group that does all this. And it's a wonderful mix of engineering students and students from the hard sciences and medical residents, medical students, and biologists interested in developing technologies for medical applications. Okay, so there. And so these are some of the things that we're working with. You can see Andrew Goldenberg's part of this. This is an MR compatible biopsy robot that we initially developed to work on doing bone biopsies, which is hard to do in an MRI scanner. But we're also repurposing this basic design, which is modular for both prostate treatment and hopefully neurosurgical interventions. And this is the MR-guided focused ultrasound machine. And it has a transducer, which focuses the ultrasound, which heats or disrupts the tissue. And it's actually a robotic system. So it has 3 different axes of motion. And of course, the MRI system itself is, in some sense, like a robotic system. And there's been a lot of interest in this. So I'm showing some of the faculty that are associated with the robotics and tools groups. And you'll notice that Eric Diller's there and Hani Naguib and others who've been very involved in this process. And Goldie, who just talked, has been on some of our graduate student committees and also as an external examiner. So our relationship with the University of Toronto is an absolutely critical one, and one I think that is going to move this whole area forward. And we have a similar type of setup for the MR-guided interventions. And I'm just showing similar groups. And it's beyond Toronto. We have relationships with the University of Waterloo, Johns Hopkins University, and University of Western Ontario, and Kingston at Queen. So I think it's a very robust way to collaborate. This slide's a little bit out of date, but basically these are the number of engineers and students we have in the lab, and we've had a very large number come through, many as co-op students from the University of Waterloo or from University of Toronto students as well. And we've also tried to get people interested at even an earlier age. So these are high school students who participated in a challenge to build a robot to do a brain biopsy using Lego Mindstorm. So my particular interest is on neurosurgical robotics. And these are the kind of procedures, and very much like the procedure I'm about to go and do, where we go into the center of the brain, I'm showing here, and try and remove something or create an opening, rather than doing a very large craniotomy where we have to remove a large part of the skull, very large incision, a lot of blood loss, there's a significant amount of risk. So we're really trying to minimize the impact we're having on patients. And so this is a view inside the brain, and this is the small tumor here that you can see that we're trying to remove. And you're going to see the instruments that we're about to use are actually quite primitive. And I'm not going to show the whole video, but so that's a grasping forceps. So we're just going to take a bite out of it and hope that nothing starts to bleed very much. And then we're going to use a tool that we're going to use to sort of take little chunks out of it. So really pretty unsophisticated. And this is basically all we can do at the moment, because if we get into bleeding, the operation can't continue, and we really don't know for sure what is beneath where we're operating on. And this is a paper that illustrates some of the problems with the tools that we're trying to develop. And so one of the areas we've been focusing on is concentric tubes. And I know that you're familiar with this, so I won't spend a lot of time on it, but we think it's one way of miniaturizing the robotic systems so that they are not only versatile, but also robust. So as you scale down a Da Vinci wrist, for example, you get to a system where either you can't build it, or if you can build it, you can't assemble it. And if you do assemble it, it'll just break, just because these things don't scale very well. So we've been looking at concentric tubes, and these are some of the design requirements, but this is what we want to do. So this is inside the cavities of the brain using a concentric tube robot to remove a tumor. And that's our kind of ultimate goal. We've had several iterations of this, and this is one of them. I think Zoe showed a simulation of this with a system somewhat like this. And this is what the versions look like. And we're using a haptic device in order to control them, building a system with a master-slave components. And this again is showing the typical instruments that we would normally use, but which are not dexterous, so scissors and forceps. And we've had some progress. So this is using the system, that's a standard peg transfer, which is pretty standard robotic test. Sorry. But this is what we can't do now. So we can't actually go in there very easily and pick something up and cut it. We just don't have the ability. We can't, we're working in parallel. It's very awkward. And with this system, we can actually do that. So that to me, I think is a huge advance. There, okay. And this is our version 3, and we build models actually of the brain. These are of patients in order to test these devices, and these are for different applications, such as for epilepsy surgery, where you want to disconnect various parts of the brain using this device. Instead of a huge operation that takes, you know, most of the day, you could actually do this very quickly through just a single small burr hole, so the patient could potentially just go home that evening. So that would make an enormous difference in so many ways. We are working on modifying these tubes to improve their mechanical performance so they don't get into these areas of high energy where they suddenly move, and developing other systems that are more dexterous but maintain significant amount of strength. And we've had a number of capstone projects through the University of Toronto mechanical engineering, which we're very pleased with. And we're using a Da Vinci as a test bed for devices. So we have a robotic system that we can just plant robotic tools on, and this is an example of one. And we actually won a competition with this, and I'll just show it to you in a second. This is a concentric tube for neurosurgery. So very pleased with that. This is at the Hamlin Medical Robotics Conference. And this is one of the capstone projects. So as I said, one of the big problems with endoscopic tools at the moment is bleeding. And at the moment, we don't have a good way to control it. And if you're working in an underwater environment, bleeding makes it very difficult to do. So this is another Hamlin Robotics challenge. And here's our bipolar, which is robotically controlled on the Da Vinci system. And we're going to cauterize lemon. So yeah, so that's the sort of tool that we think has huge promise. And this is another Da Vinci system based on these compliant tubes that are notched and have various configurations in order to make them dexterous and work and are 2 millimeters in diameter. And as I said, this is the ultimate goal. This is a collaboration we have with Boston Children's Hospital on designing a robot to work actually inside the MR, so an MR compatible robot. And this is also a recent design. This is a tool to work inside the ear. So instead of making an incision on the side of the head, you actually do everything through the, work inside the ear. And what I wanted to show you at the end, so this tool, we've actually used the tool itself, not the whole robotic system, in a single patient. So we actually have got a robot to a patient, a robotic system to a patient. And then these are other systems. This is for cleft lip and palate surgery. And again, working very hard to miniaturize the tool. So standard Da Vinci can be used in a large adult, but not in a 8-month-old infant. And so scaling for pediatrics is really important. And if you are able to scale something for pediatrics, that also means that you can use it in adults in a more minimally invasive environment. So that's one of the areas that we're working in. And we're also working on feedback. So the Da Vinci system has no force feedback. Force feedback is really hard to implement in a robotic system, as all of the robotic experts here would tell you. And that's been one of the reasons that it's had some significant complications with the Da Vinci, and that why training is so important. And this is a bone conduction feedback system that was developed for our Da Vinci test bed, which worked quite well. So it's not just the robotic tools, but also part of the feedback system. And we're also very interested in fetal surgery. So I think in the pediatric sphere, the fetus is probably one of the next frontiers. And so there are more and more abnormalities that we are detecting in utero that previously were not able to be addressed. And now, through an evolution of surgery where at about 24 weeks gestation, we can actually open the uterus and do surgery. And so we do this very frequently now for patients with biomeningocele. But it's fairly traumatic for the mother, and that they have to have 2 cesarean sections. They have to have a cesarean section from there on. They have to be delivered slightly prematurely, and there's complications related to premature birth and so on. So doing this through a robotic system is something that we would think have a huge advantage. And so here we're using a Da Vinci SI system on a very realistic model of the fetus in order to do a repair, at least in this model with a Da Vinci that would take 10 minutes. It takes in a real live fetus about 3 hours. So I think there's a real future with fetal surgery. And then also for craniofacial surgery. So these are templates to help reconstruct the forehead to produce an outcome that would be normal for that particular patient. So these are designed for the individual patient to make their forehead, which may be very pointed, for example, into a more normal configuration. And we're working on tools to do this in a minimally invasive fashion. So this is a robotic bone cutting tool that could be used for craniofacial surgery. So as I said, the MR-guided focused ultrasound system is a robotic system, and we've been working on it to develop new applications for pediatrics. This is a benign bone tumor, and this is a hemorrhage, animal model of what happens very commonly in humans that are born prematurely. So hemorrhage is a very serious complication, results in problems with accumulation of fluid inside the brain, and leads to long-term disabilities and a number of different problems. So if we could treat this non-invasively, it would be a huge advance. This is the first patient in Canada that we treated for a bone lesion using this system. And these are some of the robotic systems we're designing in order to go through an infant's skull to create lesions and lyse blood clots. This is a schematic of the robotic system that we put together. And then this is an example of the system and it's being tested. There are a lot of other applications for focused ultrasound, including doing liquid biopsies. So you can, with different energy amounts, not thermally coagulate or not disrupt tissue, but just disturb it enough that using microbubbles, it'll release tumor markers that you can measure in the bloodstream. So you don't have to actually put a probe into the brain and take a piece of tissue. We can now do this to some extent by just looking at the spinal fluid, but this way you could do it just looking at a blood sample. Motion compensation is a big problem for places outside the brain because with breathing, the diaphragm moves. And so for applications inside the abdomen, this is also really important. And making sure that the ultrasound beam is known. We're also using this for fetal applications, as I mentioned. So we're not working on robotic tools, but also non-invasive ways of treating the fetus with focused ultrasound energy. And this is a animal model. So I've run pretty quickly through all this. I just wanted to, give you an overview and stimulate your thinking about what applications we can develop for medical treatments that we can actually bring to patients. If we can't get it to a patient, it's not going to have a lot of impact. So that's also a really important part of what we do, and developing intellectual property and getting these models or devices to patients is where we want to see them. I thought you'd be interested in this. This has nothing to do with neurosurgery. This has to do with patients who are struggling on a ventilator and can't be adequately oxygenated because their lungs are extremely stiff. and it's called acute respiratory distress syndrome, or ARDS. And it's very common, and it's particularly common in patients with COVID. And so one of our anesthetists, who unfortunately passed away, developed this robotic system to treat ARDS. But when the COVID pandemic hit, we got approval to use this device in a clinical trial by Health Canada in 1 day. And so it has gone into clinical trials, and it is one of the simplest robotic systems. It's a 3D printed cage that goes around the patient's abdomen, and it's controlled by an Arduino. So that's the kind of thing I think that we can do. So I'll finish up there. I think that medical technology and medical robotics are best driven by a clinical need, and that's why I think it's important to have clinicians such as myself involved. I think this collaborative venture is the way to go, with a wide variety of experts. And there's a lot of interest in this, not only from the clinicians, but also from various graduate students, which we're really excited about. And pediatrics in particular tends to get left behind, because although you can argue children are our most important resource, you don't have to convince me of that. They are the future. They're a small part of the medical business because children are generally healthy. So we have to look after the pediatric patients and not use adult tools on pediatric patients. And I'll end there, and thank you very much for your attention.
Thank you so much.
This is very, very cool. I was trying to take notes and then I gave up because Cidnee and you are doing so much stuff.
That probably went too fast.
No, I think this gave the audience, particularly the students, the breadth of topics and the breadth of places where engineering can help, which is actually very, very useful. It's not necessarily about the sort of particular solutions, but the fact that interventional surgery can be helped with engineering solutions, both in terms of design and software throughout, is something that is very sort of anybody looking for impactful problems, here it is. Okay. So questions for anybody? Feel free to put your hand up. I can bring you up, or type your questions in the chat. While we are waiting for questions, I have a few questions, slightly sort of higher level questions. So you presented a number of these ideas based on certain ideas, let's say the concentric tube ideas, and even let's say ideas where we can have robots which have very small port of entry, and then they can, in your words, snake around. And these applications can be in fetal surgery, perhaps in neurosurgery as well. But often, this is a topic of interest for over 15 years. What do you think, or what would you say have been the challenges in this space that have prevented or limited the transition to clinician usage?
Yeah, so I think that there's a number of them. I think, first of all, these are very complex systems, and as you develop them, you begin to understand some of the limitations. And for the concentric tube ones, what I talked about briefly was this energy buildup and snapping. And you'd have to have this very much under control before you could ever bring this to a patient. So that's an example. And then there's the whole commercialization piece. And we've had one successful startup that's been bought by a NGO. But that is a very difficult road, and it's often some of the more simpler notions that can get to that stage. And so you actually have to go through this whole process of commercialization before you can actually get it to a patient outside of a research study. So you can do a research study, and that really improves, I think, your ability to demonstrate that this is actually efficacious. And then you can get other corporate entities potentially interested. I think the final challenge for all of us is going to be to prove that these are actually better. Like I'm convinced that they're going to be better, but even the Da Vinci, there are questions about just how effective it really is. And so that I think also is an important part of this.
If I could just interrupt a moment and invite everyone to turn on their video screens and join, since we're now moving into open conversation. If you need to take a break, please do so, of course. We'll be sort of formally starting the faculty AMA soon, but just wanted to take a moment to allow everybody to join us. Let's all talk together.
So we'll do the faculty AMA in I think it's scheduled for 3:45. Am I correct, Kimberly? Yes.
So Kimberly, before we let Dr. Drake go away to the OR, I have a quick question. I never heard of a One Day Health Canada approval. I really want to hear more about what does exactly the device do, and how did it go through so quickly?
Yeah, so it's a very simple device. It's a cage that goes around the patient, and it has a plastic seal, and it's built in the same concept as the iron lung. So in the polio epidemics in the 20s and 30s, they built iron lungs that created a negative pressure that allowed patients to breathe if the polio affected their spinal cord to the point that they couldn't breathe. And this is the same idea, only it's only for the abdomen. And so it just goes around the abdomen, and it creates a negative pressure around the abdomen, and that allows the lungs to expand more down into the abdomen. And that improves the ventilation in the patients. And that it came from an idea from one of the intensive care doctors who, this is a real problem in adult and children's intensive care units, is not being able to ventilate the patients, just because their lungs are filled with fluid and they don't expand very well. And the big problem with the COVID epidemic was access to ventilators. I mean, that became a problem around the world. There just weren't enough ventilators in the areas that got really hit hard. And these patients tend to be on the ventilators for a long time. And so they can be on the ventilator for 2 to 3 weeks. So something like this could have had a dramatic effect. And I've never seen anything approved by Health Canada either. I mean, the clinical trial was kind of all ready to go. And as I mentioned, unfortunately, this individual passed away at a young age, but it was ready to go, and then one day it was approved, and so it went off into clinical studies.
Well, wonderful. I think it shows again simplicity and functionality are most beautiful. It's useful stuff. Thank you.
Jim, a great talk. Thank you for telling us about all those great projects. I'm wondering if you could tell us about what kind of training you give to your engineering students, which might be interesting for, I think most of the people here are engineering students. What kind of training do you give them in procedures or medicine to have them be effective for working on these projects?
Yeah, so I think that there's kind of 2 areas of knowledge that don't overlap all that much, and that's the anatomy and physiology of the human body, and then there's the engineering sciences. And so many of the engineering students that come to us, they take a course in anatomy or physiology or medical applications or imaging or something like that. And I think more importantly is we partner in the lab. There's this mix of medical and engineering students, and they, I think, cross-fertilize information very well. We used to be able to bring students into the operating room fairly frequently. That's all been changed with COVID. There is video monitoring that they can have access to, but and by the same token, many of the medical students that come our way, not medical students, but medical surgical residents and so on, they often have an engineering background, and so it's not the same as someone who's a postdoc from an engineering PhD thesis, but nevertheless, they do have a fair amount in common, and they can cross-communicate pretty effectively. And then the other model that Eric, you know so well, is that we often have co-supervision between, medical individual and an engineering faculty. And that sort of covers both bases in terms of supporting the students in making sure that, that the knowledge that they need to do their thesis is, sufficient, and that they have access to people that they can go to get the information they need.
Yeah, great, thanks.
So we have one final question that is from non-engineers, and I think that would be a good idea. So Amy asks, as a public health educator who is not an engineer, how do you recommend we build public trust or patient trust for use of such cutting edge technology? And is there any resistance from such usage?
Yeah, it's a very interesting question. It's usually the opposite, and patients want the latest technology, unproven or not. And so, I think to an extent, right? So, lasers and, the Da Vinci robot, a lot of it is, someone with prostate cancer, they've heard all about the robot and they want to have their procedure by a robot. I think the bigger challenge will be when we get to autonomous robotics. So I think that will be different, right? So if there isn't actually a human being who's not actually doing the surgery, but is supervising a robot, that I think will be a much bigger challenge. I think that the self-driving cars, I think that's going to help with this, but I think that it will be our duty to make sure that we can demonstrate that these are actually safer than than having a surgeon do the procedure. And this technology is also kind of all around us. So the jets are all landing themselves, right? The pilot's not actually landing the plane, and so I think as more and more of that becomes sort of ingrained in what we're doing, I think there'll be more acceptance. But there are levels of autonomy that are obviously easier to implement, but like full autonomy, I think that'll be a huge regulatory, but as has been mentioned also, I think a social hurdle.
It's wonderful that you mentioned autonomy. So one of the things that I am particularly curious about, and a number of hopefully students who are now interested in AI and computer science, or basically just software, that a number of advancements that you described today were design advancements. How can we build better tools to solve these problems? What is the role of autonomy in this?
Well, because I think that you can build tools that are actually better than a human, and particularly at smaller scales. And you can implement things like virtual fixtures that prevent a human from accidentally straying into an area that they weren't cognizant of. And so, I think you can design tools that are actually safer than a human. And so that I think is an important challenge, and I think that's where this eventually is going to head. I think it's going to take much longer than we probably think, but yeah. So I think there is going to be a real role for autonomy, and but I think it's going to be obviously at different levels, and having virtual fixtures is, I suppose, not autonomy, but it is a control system which constrains what happens and would be very much part of an autonomous system.
While I believe that this is going to be a very wonderful conversation, but I would like to thank Dr. Jim Drake for providing us his valuable time coming out. And I believe all of us enjoyed this talk. So thank you. Thanks a lot, Jim.